Okay, so the last part of this module deals with the use of Matlab to plot, or Bode plots, to create Bode plots, which is this plot of an S-domain function in the frequency domain, so where we limit our S-domain to just the imaginary axis, so S is equal to j omega. And so this can be done quite easily in Matlab, because Matlab can deal with complex quantities very easily. So we can define a omega. This is the range of our frequency. So if I use 2 pi times the log space, so this is representing the frequency, and I multiply that by 2 pi to get my omega, which is the frequency, radian frequency, or in rads per second. I can very easily calculate my h in terms of omega, so it's simply just plugging that into, or typing that into Matlab using the dot operator, since omega is a vector. So h is also a vector, which will have 1,000 points. And then we can use the semi-log x to represent and plot the absolute value of h, or we could use it to represent and plot the phase of h. So each one of these can be created in exactly the same way as these three statements defined above, where we define an omega given by this range, and you could either use lin space or log space to do that. Log space uses the coefficients of 10, so in this case, for this problem here, the log space definition would be -3 to 3, so log space -3 to 3, say with 1,000 points, something like that. And then you can type in your g using j omega, and then you can calculate your g at every value of omega, which is defined by that log space function. So so this last part is using this transfer function of this circuit from application exercise number 1, the same circuit given above. And so what we'd like to do is plot this for the two values of RL that we found in part C and D. So this is going back to this idea of what value of RL produces this result. So this is the first one. The second one is 1,000 ohms. So if we take those and we plot this transfer function for those two values using all the other R, S, L, and C values in RC that we've been given, then we can take a look at the transfer function and see how this changes. So this is the frequency from 10 to the -3 rads per second to 10 to the 5 rads per second. And what we find is that at low frequencies, these two responses are about the same. So the output voltage is about the same as the input voltage in terms of magnitude. And then for RL is equal to 1,000, which, just to remind you, is the case in which we have these damped cosine and a cosine. So we have this oscillation, we have this underdamped natural response. We have this huge peak that happens around this frequency, which relates to the circuit elements. And in the other case, where we have the underdamped or the overdamped response, where our response is just the forcing function cosine and the natural response is these two decaying exponentials, so this is an overdamped response, we get this fact that there's no peak here. So this peak is due to this underdamped response, and which causes this oscillation to appear at the output. So quite interesting that you can see such a big difference in the Bode plots for these two values of RL.